Okay, section 4.3, it's more work with polynomial functions, talking about roots and how to find them mostly. But let's start out with kind of a formal definition of what the function looks like. Basically, you'll see this in the book. These subscripts, it just means that you have a coefficient that goes along with the x to the nth term. Could be x cubed or whatever. It's just matching them up. Then you have a coefficient that goes with the next term down. Notice how they go in descending order. This is standard form right here. And all the way down to the first one, and normally we don't write x to the first power, we leave the 1 off, but anyways, there's a coefficient in that, and then a0 stands for the constant term. It's called a0. So basically this just shows you can have any number of terms in these things. You can have real numbers, you can also have complex coefficients. However, we're not working with those, so everything we're doing, all the tests that we're going to use and everything, we're just working with real coefficients, okay? Now, we might get complex roots, that's fine, but we're working with real coefficients, otherwise things change. Okay, again, we've talked about the zeros of a polynomial. Okay, the zeros just means that I put in some number for x and the function equals 0. Okay, so what does that mean? That means I would have a point, whatever that x value is, and the y value would always be 0. That also means, again, when y is 0 this way, that means we're on the x-axis. So what that means is zeros are where a curve either crosses the x-axis or at least touches it. And we saw that with sometimes parabolas will touch it, but that's still considered an intercept point on the x-axis. Okay, another thing, we talked about this before, the number of zeros, or factors even for that matter, equals the degree of the polynomial. And let's just say degree of highest term. So if you got them in descending order, that's going to be the highest term. So look around, whatever the highest degree is, that's the degree of the polynomial. So if that was a 7, I'd have 7 zeros. Now, again, we already talked about this. They may not all be unique. You could have distinct zeros, they might repeat. Okay, that's fine, but they're there. So let's look at an example of that. Again, that's my polynomial. That's the degree of the polynomial because it's the highest degree there. Also, that means I'm going to have 2 roots. However, if you factor this thing, it looks like this. So it looks like you have 1 root, minus 2, but it appears twice, so the terminology they use for that in this case would be multiplicity of 2. So a root can have a multiplicity. Multiplicity of 3, it would occur 3 times. Multiplicity of 4, 4 times, and so on. If it only occurs once, then we don't use a special name for it. Okay, what about complex roots? There's something special about those. You remember complex roots. This pencil's driving me nuts. That's the a plus bi kind of thing. Imaginary portion, a real portion. If you have a complex root, so let's say a plus bi could be anything, then the conjugate is also a root. They come in pairs. So you also have the conjugate. Okay, so suppose I have p of x. I don't know what it is. Somebody tells me, hey, look, 7 minus 4i is a root. I immediately know then that 7 plus 4i is also a root. Again, with the conjugate, just change the sign in the center and you've got it. So, conjugate roots come, or complex roots come in conjugate pairs. Okay, and we'll use that later on. Right now, that's all we're going to say about it. We have another interesting theorem here. It's neat, and visually, I think you can figure it out, but it's not super powerful. And that is the intermediate value theorem. Kind of like it sounds. I have a polynomial function, and let's say I have a couple of values here, 2 different a's. Let's say I check it at some value of a, maybe it could be p of 4, 5, whatever. Anyways, if that comes out to be positive, and I test another value, and it comes out to be negative, or vice versa. In other words, one's above the axis and one's below the axis. Well, then obviously there's a 0 between these two. So just a 0 exists between them. You can see this. I mean, this is pretty basic. If we had a graph here, and I checked here, say that was p of a, and that was p of b. This is positive, this is negative. Obviously, to get from above the x-axis to below, you got to cross it. So you're going to have a 0 between those 2 points. But it could be more than one 0. So a 0 or more zeros exist, because let's say, for example, I checked this one and I wanted this interval here. Well, in this interval, no, I can't do that. I need to check it here. Sorry. We don't get any information here. We're not sure. Let me erase that. Okay. So, suppose this is my interval. It tests negative here, but when I plug in this x value, it's positive. So I know there's a 0, but in fact here there's 1, 2, 3 zeros. So all this theorem really says is if you're above and below the axis, within an interval, at the edges of an interval, then you got at least 1 0, but that's all. You don't know how many.